All right, gang, here we go. This is for Physics, Unit 7, Part 3. We're talking about wave interference. Okay, so last part, we talked all about waves and wave properties. We talked about how to talk about how waves move through mediums and what's really causing them. We talked about some new terminology. A lot of what we talked about should have been reviewed from chemistry and from physical science, right? But now we're going to get into some new ideas here that you probably haven't thought about before, and that's the idea of how waves interact with one another in nature. Okay, and this happens all the time. So much so that it has its own special name. It's called superposition. All right, superposition is the combination of two overlapping waves. And there are very specific rules that dictate how superposition occurs. Okay. Now the cool thing about waves, and one of the things that gives them a thing that defines one of their main properties, is the idea that waves can occupy the same space at the same time, more than one wave. Like for example, right now, if I turned on a radio, I'd get a whole ton of radio waves. They're here right now. I just can't interact with them. Those same radio waves, there's light coming from my light right now. That is also a wave. There's waves from my voice that are going out, being captured by the microphone. There's all sorts of waves that are occurring right now, right all at the same time, right around me, and they're all occupying the same space all at the same time without any sort of collision or anything like that going on. So that's one of the things that really makes waves kind of really bizarre, and can make waves be very complicated very quickly. We're just going to barely skim the surface of some of these wave interference ideas in this video, okay? And we're just gonna, and then as we move through the next couple of units, we're really going to delve deep into what happens with waves and take these ideas a little bit further. But anyway, so when waves hit each other, you get what's called a resultant wave or a composite wave. And so it's this wave that is a combination of the two waves. Okay, so as waves pass through each other, they form what's called the composite wave. And if you want to, you can watch this. I'll just mouse over that. You can pause it and watch it if you want. All right. Now, the first way it can happen, first superposition of waves that you can have is called a constructive interference. Constructive interference occurs when the two waves that are hitting each other have displacements in the same direction, or their amplitudes are both positive or both negative. So here we've got this set of ropes, right? The set of rope with two waves that are headed at each other. This bigger one is headed to the right. This smaller one is going to the left. Okay, and then they're going to go towards each other. Right, and so this is the picture of what the rope looks like once these two waves are close to one another. Now the darker rope, that's what the shape the rope is actually going to make. So this is the first sign of our constructive interference. This grayed out rope, this is to give you an idea of what those two ropes would have looked like had the two waves not superimposed on one another. Okay, and then right when they're on top of each other, we get constructive interference, and these two ropes, their amplitudes add together in order to make one big amplitude, and so that's called constructive interference, where these two ropes, these two waves interfere with one another, they superimpose. Okay, and then you get this taller wave, and then after the wave moves through, okay, the crazy thing is these two waves move on as if that superposition never occurred. Okay, so the smaller wave that was on the right remains unchanged, it just keeps going to the left, and the bigger wave that was on the left just keeps going to the right, just as it was. Okay, notice that these amplitudes are exactly equal to one another. Pretty bizarre. Okay. Now, destructive interference is the opposite of constructive interference. It's when these two amplitudes of waves are in opposite directions. So here, the one going to the right has a positive displacement, and the one going to the left has a negative displacement. Okay, notice that as they come towards one another, they start interacting with one another, and then once they're right on top of each other, look what happened to the amplitude of the resultant wave. It got less. Notice that the distance that it dropped down is equal to the sum of this positive and negative from these two amplitudes. Okay, and then after the interaction occurs, they keep going on their merry way as if nothing ever happened. You could imagine a situation where the two waves have the exact same amplitude, but in opposite direction, and so your rope would make a completely flat line. Pretty bizarre. All right, so that's destructive interference. Okay. Another kind of wave interaction that you need to know about are reflections. Okay, reflections occur when your medium hits some sort of barrier and cannot keep going in the same direction it was. All right, so the first type of reflection here is a free end reflection. So the rope here is tied to some pole that it can move up and down on. Okay, and so they flick the rope, this pulse has traveled to the right, and then as it hits this post, okay, the rope can go up and then come back down. And when it does that, the reflected pulse is in the same direction as the incident pulse. Okay, so they both have a positive amplitude in this way, in this case. Okay, so the reflected pulse is upright. So this is what happens if your reflection has a free end. In a fixed end, the reflection is inverted. Okay, so the incident pulse comes in, and then this part is fixed. It cannot move. So when it gets reflected, it comes back opposite of the incident pulse. So it's inverted the other way around. Okay, so and so this is our fixed end. All right. Now, you could imagine a case where if you had a string, right? So imagine we had a string like a guitar string. Oh my gosh. So there's our string. Stop it. Okay. Okay. There's one end of our guitar string that we've tied down. Okay. And here's the other end of our guitar string that we've tied down. Okay, right here. And you could imagine a case where if you've taken and you start a pulse that goes along this way along our string, it's going to go and it's going to travel to the right over here, and then it's going to hit this, and because this is stuck, okay, it gets inverted. We just talked about how this reflection inverts it, so it's going to go back the opposite way. And so if we send just a pulse, then this would go out and it get reflected back this way, and then it reflect back that way, and you get stuck like that. However, if we send a periodic wave, or a wave that obeyed simple harmonic motion, then we'd start this standing wave, or this wave that would kind of go out like this, right, like this, and then it hit the end, right, and then it would get reflected back at us, right, like this. And so, and as long as it was periodic, if it kept going, these two waves would start interacting with one another, right? And so you'd end up with a new resultant wave, okay, where you'd have what's called a standing wave. Okay, and a standing wave occurs when two identical waves travel in opposite directions and then interfere with one another. And so you get this new standing wave that alternates between destructive and constructive interference. Okay, and so a standing wave, so this is just one example, and we'll look at a picture on the next slide that has tons of standing waves. This standing wave that I drew is not necessarily based on this that I first drew. Okay, so ignore this now. Okay, so now the standing wave, now it's called a standing wave because this wave, it doesn't look like it travels from right to left. It looks like it just sticks the way it is, just like this. All right, but really it moves up and down. Okay, it goes from this to this, and I'll draw the other side of it with a dashed line, so it would do something like this. All right, and so this wave would kind of go up and down just like this. All right, so this would be our standing wave that flip backs and forth, flip, flop, flip, flop, flip, flop, back and forth like this. So they're called standing waves, but they move. Okay, so they don't stand still, but really they just kind of flip flop back and forth. Now notice how this part flip flops, but in both waves I drew it where this spot right here doesn't move. Notice how in both the dashed wave and the solid wave, this spot doesn't move. This is a spot where you have complete destructive interference, and the wave that was traveling to the right gets completely canceled out by the wave traveling to the left. Okay, and so we call this a node. Okay, so this is called a node, and I like to think it's like it says no, so it means no movement, nodes. Okay, so it's stuck there. All right, and then notice that here you've got a lot of movement. Okay, these are known as antinodes. All right, so it's a double negative, anti-node, so it's a lot of movement. Okay, and so this guy moves up and down, and so this is a place where you have complete constructive interference. Okay. All right, so nodes are where you have destructive interference. Antinodes are where you have constructive interference. Okay, and so this sets up a standing wave, and standing waves are really, really important, especially for musical instruments. If you've ever taken like a pop bottle and blown across the top, and it makes that hum sound, that is a standing wave that you've started in that pop bottle. Okay, if you've ever played like a trombone or a trumpet or the piano, you're creating standing waves on the whatever instrument that you're playing on. Okay, so these are standing waves. So here's an example of standing waves. Now notice here, there's a couple of things that I want you to notice. So here is just our string that we have. This is essentially what I just drew. Okay, now notice that in all these waves, they all have something in common. In order to create a standing wave, the frequency and wavelength that you create always has to be such that you have nodes at the front and the end, or the beginning and the end of your string. Okay, now remember that a wave always makes a shape like this. Okay, and it kind of keeps going like this. All right, and so this would be our middle point like that. Okay, sorry for my artistic abilities, it's rough, huh? Anyway, and so we've got these nodes. Okay, now in order to make a standing wave, remember we just said that we have to start and end on a node. Okay, and so we end up making these specific shapes based on that fact. Okay, so the first wave right here, it's also called the fundamental wavelength. Fundamental wavelength. Okay, this fundamental wavelength is based on the idea that we have to start and end on a node. All right, so this, if we start right here, I'm going to start drawing X's instead of circles. So here's our node, our first node, and so the first other node that we can have is this guy right here. All right, and so the shape of our wave is this. Now think for a second, what would be the wavelength of that wave? Well, we know that by definition, an entire wave would be going from here, this spot, all the way to this spot. Well, we had exactly half a wavelength here. So the wavelength of this wave here would be equal to 2 times whatever length our string is. Okay. This one here, all right, so the next wavelength we could have would go to the very next node. So it would be from here all the way to the next node, and our wave would go all the way from here and then to here. So notice that's exactly what we drew. So we'd have 3 nodes and 2 antinodes. All right, and what would the wavelength be? What would be one full wavelength? So our wavelength is equal to just L. All right, and then let's do one more here. So then the next node that we could go to is this guy right here. All right, so we'd go up, down, and so we'd have 4 nodes and 3 antinodes. So the wavelength would be exactly 2/3 of this length. 2/3. All right, hopefully I'm not blocking it with my face. I am a little bit. All right, so 2/3 of that length. All right, so these guys here are different wavelengths, and this is really what determines what kind of music or what kind of notes you can play on whatever instrument. So like I play trombone, all right, and so on trombone in first position, the lowest note you can play is a B flat. All right, and that's at that fundamental wavelength. The next note you can play is an F, and that F is the next note you can play because that is the next value or the next wavelength that makes it so I have 2 nodes on my standing wave that I'm setting up in my trombone. The next note I can play is a B flat, and then you can keep going from there. And it's really all determined based on the length of the horn. That's why a lot of instrumentation is really just based on how long is your string, how long is your thing. A trombone works on the fact that as you move your slide out, okay, you're really just making your standing wave longer. And because you're making it longer, you can have longer wavelengths and you change that pitch. That's why tones go down as you go out. You know, everybody knows that sound. Trombones made the right? That sound. If you've been in 5th grade band, you've heard trombones do it for hours. Okay, if you've played guitar, you strum on that guitar and you play, and you've got a length, and then you press a fret. You've made that length shorter, so now it's going to vibrate at a different wavelength because it's setting up that standing wave. All right, so this is really important as we move forward into sound, especially this idea of making standing waves. Okay, and that's about it. If you'd like, you could watch this. It just kind of animates exactly what we just showed. All right, but it does a pretty good job showing those animations. Okay, so do you practice problems? Let me know if you have any questions, and I'll see you on the flip side.